All right, moving on to our last bonding theory. Valence bond does better than Lewis at predicting some things like bonding schemes, bond strength, bond length, bond rigidity, that sort of thing. But it doesn't predict other things well, like the magnetic behavior of oxygen. And it's assuming that electrons are localized in orbitals on the atoms. It doesn't account for delocalization, which are electrons that are spread throughout the molecule. So from there, we go to molecular orbital theory. What happens in molecular orbital theory is Schrodinger's wave equation is applied to the whole molecule to calculate a set of molecular orbitals. Now remember, when we get more than one electron involved, we can only estimate the solution. And here we start with guesses about what the orbital should look like and then minimize the energy. Here, electrons belong to the whole molecule and the orbitals belong to the whole molecule, which allows for delocalization. The simplest of the molecular orbital theories is called LCAO, linear combination of atomic orbitals. It's a weighted sum of the atomic orbitals. And because our orbitals are wave functions, our waves can either combine constructively, which if you remember, that means a wave plus a wave, they're in phase, and we get a bigger wave. Or they can add up destructively, which is where we have a wave, and they add up to nothing. When our wave functions combine constructively, we get a bonding molecular orbital, which allows for most of the electron density to be between the nuclei. When the wave functions combine destructively, we get what's called an antibonding molecular orbital, which has most of the density outside the nuclei and a node in between the two nuclei. Here's a picture for you. If we're looking at the interaction of the 1s orbitals, if they interact destructively, we get a antibonding molecular orbital. We always indicate antibonding with the star. That means antibonding, where you can see right in between there's a node. Destructive interference happens. When there's constructive interference, we get the bonding molecular orbital, where there's lots of electron density in between the two nuclei. In molecular orbital theory, electrons in bonding molecular orbitals are stabilizing. They have lower energy than the atomic orbitals. The ones in antibonding molecular orbitals are destabilizing because they're higher in energy than the atomic orbitals. We can predict bond order by taking the difference between the number of electrons in bonding and antibonding orbitals. We only need to think about valence electrons, and this could be a fraction. The higher the bond order, the stronger and the shorter the bond. If bond order is 0 or less, then the bond is unstable compared to the individual atoms and a bond won't form. Also, if we have these molecular orbitals, we can learn about a substance being paramagnetic. If we end up with unpaired electrons in a molecular orbital, then the substance is paramagnetic. If all the electrons are paired up, it's diamagnetic. Let's look at a simple example. For hydrogen, we can combine our, we can create molecular orbitals from the 1s orbital, the linear combination. We get a sigma orbital that is lower in energy than the two atomic orbitals. We get a sigma star antibonding orbital that's higher in energy. We're adding 2 electrons. Those 2 electrons go into our sigma bonding orbital. So we have a net bond because we have more electrons in a bonding orbital than in the antibonding. For helium, if we were to use those molecular orbitals, now we have 4 electrons to account for, and we're going to end up with 2 electrons in the bonding orbital and 2 in the antibonding. Because we have the same amount of electrons in antibonding as in bonding, there's going to be no net bonding interaction. So helium does not form a diatomic molecule. What about lithium? Here we have to add in those 2 s orbitals. For the core electrons, your bond order is going to always end up being 0 because you're going to have the same number of electrons in the bonding and the antibonding. So we only generally look at the valence. So our valence electrons here, we get 2 in a bonding, none in the antibonding. So yes, dilithium can form. What about p orbitals? Here's, remember what the atomic orbitals look like. The antibonding has this node in between the 2 nuclei. The bonding has the interaction in between the 2 nuclei. So the bonding is lower in energy, antibonding is higher. And that happens along all 3 axes. So you can get the, the previous slide was the sigma. Then there are also pi bonds. We can have the pi 2p and the pi star 2p, the antibonding. And again, you can see for the bonding, there's interaction above and below the nuclei in this case. And then the antibonding has that big node in between. Same for the z-axis. Now, what order the molecular orbitals go in depends on what atom you're looking at. So that has to be determined based on the atom. So for this class, we're going to give you the molecular orbitals and the order of them. For boron, carbon, and nitrogen, the pi 2p is lower than the sigma 2p. But for oxygen, fluorine, and neon, the sigma 2p ends up lower than the pi 2p. So yeah, that's just dependent on the atom itself. There's no way to know that without doing a lot of mathematical simulations. Let's talk about oxygen. O2 is paramagnetic, which means if you pour, so this is liquid oxygen. If you pour it between a magnet, it aligns itself to the magnet and will stick in between there, which means there have to be unpaired electrons, because paramagnetic, the definition is that there are unpaired electrons. We don't see that in Lewis theory or valence bond theory. But if we look at the molecular orbitals, so this is Lewis theory and valence bond theory, everything pairs up. But with our molecular orbitals, if we fill in our valence electrons into our molecular orbitals, we have we have 12 electrons to account for. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can see that in our pi star up here, there are 2 half-filled molecular orbitals, which leads to the paramagnetic behavior. Then our bond order, to calculate bond order, you're going to take 1/2 of times your bonding electrons minus your antibonding electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons. 1, 2, 3, 4 antibonding gets us a bond order of 2, or the double bond that we see in dioxygen. Let's practice. Draw a molecular orbital diagram of N2- ion, predict its bond order and magnetic properties. So here I have drawn out the molecular orbital diagram. This is from a couple slides ago, and it's based on the one that dinitrogen would use. we have to count our number of valence electrons. So each nitrogen is going to bring 5 valence electrons, and then we have one more for our minus there. So we have 11 electrons to account for. And then we can just fill in our molecular orbitals the same way we would atomic orbitals, following Aufbau, Pauli, and Hund's rule. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. And then it says predict bond order and magnetic properties. So our bond order is going to be 1/2. Our bonding electrons, we have 2, 4, 6, 8, minus 2, 3. So 8 minus 3 is 5. So our bond order is 5/2. So there's that. And then I didn't have the final answer on there. Okay, next, draw a molecular orbital diagram of C2+, predict its bond order and magnetic properties. So I would recommend pausing, working through this yourself. We have the diagram there on the left. So C2+, each carbon comes with 4 electrons, but then we're subtracting 1 for our plus there, so we're going to have 7 electrons to account for. 1, 2, 3, 4, 5, 6, 7 electrons. Our bond order is going to be 1/2, 1, 2, 3, 4, 5 bonding, minus our 2 anti-bonding. So our bond order is 3/2. And we have 1 unpaired electron. So we're going to be paramagnetic. That's the same for the nitrogen. I forgot to mention that, but there was an unpaired electron there, so that one is also paramagnetic. All right. So what about if we have atoms that are not the same bonded together? When you're combining atomic orbitals of different types in energy, the atomic orbital closest in energy to the molecular is going to contribute more. And the more electronegative the atom, the lower the energy. Then our non-bonding molecular orbitals are going to remain localized on the atom that's donating. So let's look at an example. I think that's far easier than talking through all of that. So hydrofluoric acid. Fluorine is more electronegative, so its electrons are going to be lower in energy. We're going to combine one of our p orbitals from fluorine with one of the 1s orbitals from the 1s orbital from our hydrogen. So we're going to get this sigma orbital there, which is where the bond is, and then we end up with non-bonding orbitals that are the same energy as the p orbitals that they came from. When we get to polyatomics, you really need a computer program to deal with this. It's going to give molecular orbitals that are delocalized, and if you can do it, it gives a much better match to real molecule properties than Lewis or valence bond theory. But like I said, things get complex. Here's some examples. Ozone, in valence bond, you just have a pi bond between 2 of the oxygens, and you have this resonant structure here. Molecular orbital, if you look at the orbitals, they are delocalized over the whole molecule, which explains its properties better. Okay, one last multiple choice question. According to molecular orbital theory, which of the following will have the shortest bond length? Well, we can fill in our orbitals there. Our C2, we're going to have 8 electrons to account for. C2 plus, we have 7. C2 minus, we're going to have 9. So let's fill in 1, 2, 3, 4, 5, 6, 7, and then our extra one here for our 8, and our extra one there for our 9. So our bond order for our C2 is going to be 2, 4, 6, 1/2, 6 minus 2, which gets us a bond order of 2. The 7 electron is going to be 1/2, 5 minus 2, which is 3/2, so less. So logically, our C2 minus is going to be greater because we have one more electron in a bonding orbital with with the same number of antibondings. So our bond order there is going to be the highest, specifically 5/2, and a higher bond order leads to a stronger bond, which is a shorter bond length, which is what my question was asking. So the answer is 3 C2 minus.